First, I would like to thank a lot the organizers, not only for organizing this workshop, but also for organizing this long-term program, which so far I really enjoy. Also I would like to thank them a lot for giving me the opportunity to present some of my results here. So this, what I will present here will be based on several collaborations together with Nils Behrmann, who is a master's student in Bonn, Christian Brennecke, who is also at the University of Bonn, Phan, who is in Munich, as I am, and Lorenzo, who I guess you all know, and Daniel Wiroszek, who will come for the second workshop to this program. So as the previous talk by Andreas Deuchert, I'm also from the same mathematical physics community, so I'm also working in the mathematical analysis of many-body quantum systems. So let me maybe first start with giving, again, a short introduction about what we are actually interested in this research area. So from a physical point of view, there are several systems, such as a gas of a lot of interacting atoms, that are interesting to study, where we have a large number of interacting particles. And by the basic principles of physics, they are described by, so the dynamics of such system, for example, by the solution of a many-particle Schrödinger equation, or by the ground state of a many-body interacting Hamiltonian. The problem with these microscopic description is that in order to understand the whole system, one would need to really analyze basically all the individual interacting particles. And because the number of these particles is very large, this is hardly accessible to gain any information about this system. So what we are interested in now in the mathematical analysis of the system is to, instead of looking at all the individual particles, to look at the macroscopic behavior of the collective behavior of the particles, and to look for a macroscopic description of this collective behavior of the particles in the large particle limit. So here we are always interested in sending the number of particles of the systems to infinity, and then arrive at an easier, accessible, effective description, which will often be given by a one-particle effective dynamics, or the ground state of a one-particle Hamiltonian. So this is the overall idea of what we are doing basically in this many-body community. And so the goal is to find a mathematical rigorous way to formulate these approximation. So on the one hand, to really formulate this approximation in the mathematical rigorous sense, but then also to study the properties of the system based on this macroscopic, much easier description. All right, and so my talk, that's the structure for the rest of my talk, because what I want to do now is to make this precise for one specific many-body system that I'm going to study, namely the Bose gas, as was already my title. So first I would like to give a physical motivation again, why this was already partly done by Andreas, why it is interesting to study these Bose gases. Then I will briefly introduce you to the mathematical description of the Bose gas, to be then able to state our main result, namely the large deviations that we get for weak mean field interaction of the particles. Then I would like to briefly sketch the idea of the proof and formulate as an outlook what we are able to show in the case of more singular interactions, which are more relevant from the physical point of view. And also what we can say about empirical measures associated to these Bose gases. Okay, so let me start first with the physical motivation, why we are looking at those Bose gases. So it was predicted in 1924 by Bose-Einstein, so this is where the name comes from, that a gas of a large number of interacting bosons show a very particular phase transition at low temperatures. So as Andreas already described, one expects that at room temperature, the gas behaves like an ordinary gas. While when you cool it down to very low temperatures, then most of the particles condense into the same quantum state and behave as one giant unique quantum wave. And it took the physicists roughly 50 years to observe these phenomena also in experiments. So this was done by the working groups of Cornell, Wieman, and Ketterle in 1975. And what they did was to take rubidium, respectively sodium atoms. They trapped them with some external potential, cooled it down to very low temperatures, released the trap, and measured the velocity distribution. And what you can see is the result here. So that's the velocity distribution where the gas was cooled down from the left to the right. So the cooler the gas is, the more particles have the same velocity in this distribution there, which physically means they are in the same one quantum state. Right. And we want to describe this phenomenon now from a mathematical point of view in the following sense, namely from the basic principles of physics. These Bose gas is described by an n-particle system, so these n bosons that are interacting. And what we are interested in is this large particle limit, and we want to argue in a mathematical way that we can approximate our n-particle system by an effective one-particle system, namely by these condensate wave functions that we from the physics experiment expect most of the particles have condensed into. And the way how we want to formulate this mathematically in the following is through law of large numbers, and then later also through large deviation principles. So basically, going back to this velocity distribution, what we want to do in the end is that we want to analyze the tails of this velocity distribution that we can see here on the slide. Okay, so let's start with that. For that, we first of all have to go a bit more into details how we mathematically describe our Bose gas. So it's a bit similar to the setting that Andreas was also mentioning, but here we really consider so fixed n bosons, and we consider them again that they are living on the being restricted on the unit torus with periodic boundary conditions. We want them to have satisfy the bosonic statistics, so they are in the symmetric subspace of L2 function of the unit torus, and they are described by the energy functional that you can see here. And the energy consists of two terms. So here we have the kinetic energy of the particle that is simply the sum of the Laplace operator acting on all the n particles. And then we have an interaction term. As you can see, it's a two-body interaction. So the sum runs over the indices I and j. And it depends on the position of the ith and the jth particle. So in order to make both terms compatible, we put these 1 over n factor in front of the interaction term so that they have the same scaling order. This is in physics often called the mean field regime. So one expects that the particles expect a lot of weak, a large number of weak mean field interactions. Okay, so in order to describe the experiments, so what the physicists did in lab was to trap the system. So the trapping we sort of described with the trapping our bosons on this unit torus, and then they cooled it down to very low temperatures. So here we consider the idealized situation where we are really at 0 temperatures, so which means that we really consider the ground state of the system. So psi-n in the following will be the ground state of these n-body interacting Hamiltonian. Okay. And what we want to describe from the previous slide was this probability distribution basically of the velocity. So what we are interested in is on measuring or realizing observables, which are mathematically taken care of operators. So O in the following will be a one-particle operator. And then we call OI an n-particle operator that acts as identity on all the particles, but the ith where it acts as this operator O. And from a mathematical perspective, we can understand OI as a random variable, where the law is given by the ground state that we defined before. So the probability of these random variable OIM taken values in the real valued set A is given by the expectation in the ground state psi-n of the characteristic function of the set A of OI. Okay, so this is very nice. So we have an explicit expression for the law of our random variable. However, what is a bit nasty about that is that it's though it's explicitly given, we do not really have precise knowledge how this looks like, because it's formulated with respect to these the ground state of an n-particle interacting Hamiltonian. So we do not really have good knowledge on this probability distribution, how it looks like. Also, maybe to get a better feeling what these about this definition here, maybe let's start with or have a look at an easier example. So instead of considering the ground state of these interacting Hamiltonian, we can also start, like for the moment, take the same definition, but then now have a look at the purely factorized state instead. Because then we will see a lot of things get more easier. So if we take the same probability distribution that we had on the previous slide, but with respect to this purely factorized state, we can compute the expectation value of our random variable ONI with respect to this probability distribution, and that's simply given by the expectation of OI in the state phi to the n. But this we can explicitly compute because OI only acts on the ith particle as O, otherwise it acts as identity, so this is a normalized state, so this is simply the expectation value of O in the state phi. That's fine, but this is also the same as the expectation value of the operator ONJ. So in particular, they are identically distributed, the random variables ONI and ONJ, which is nice. Okay. Second, what we can also have a look at is the expectation value of ONI and ONJ, where I is not equal to j. And that's also easy to compute. Right? Because they are not the same. So, okay, this was too fast. So the ONI only acts on the ith particle, ONJ only on the jth particle. So this is exactly the square of the expectation of phi of O. Okay, and that's the same as we see in the first line as the expectation of ONI and times the expectation of ONJ. So which means in this setting where we have really a purely factorized state, our random variables are not only identically distributed, but also independent. Okay, so, but this was for this very special case of this purely factorized state. So let's go back to the state we are actually interested in, namely this ground state of these interacting Hamiltonian. And there it's a bit different. I mean, we can still have a look, what is the expectation of ONI? We can write it again, simply by definition, as the expectation of OI in the state psi n. Since we have these bosonic statistics, so the particles are symmetric whenever I permute them, this is actually the same as the expectation of ONJ, simply by the symmetry property. Which means that even then in our, like if we consider now the ground state, we have identically distributed random variables. However, what is not true anymore, that the expectation of ONI and ONJ is the same as the product of the expectation of ONI and ONJ. I forgot an n here. Simply because they are not, the ground state is not a purely factorized state. And this is because there are some correlations, some quantum correlations come into play. Which means the random variables we are interested in are identically distributed but correlated random variables. Okay.
But the probability law is associated with O, right? The law is associated with O. And O is the random variable. I mean,
O is the random variable whose law is given by the ground state. Yes. So like I fix an operator O and I fix the ground state, right? And then I define these random variables. Yeah. Still, if we think back of the physicists' experiments, what they somehow got was that most of the particles are, or what they expected or measured, that most of the particles are in the same one-particle state. So though we don't expect that the ground state, or we know the ground state is not a purely factorized state, we still hope or expect that most of the particles actually are in these condensate wave function. And there's a mathematically rigorous way of formulating that, namely in terms of a law of large numbers. And this is something which is mathematically often also called Bose-Einstein condensation, namely that if we sum over all the ONI from I, so the sum runs from I is 1 up to n, and average with n, and subtract the expectation of the operator O in the condensate's expectation, then this guy converges in probability to 0 in the large particle limit, which basically says exactly that what the physicists were observing, that most of the particles are in this one particle state. So though we have correlated random variables, the correlations are not strong enough to destroy the law of large numbers in that sense. And this was proven by Lieb and Saringer in 2002, together with some arguments that Behrmann, Kirkpatrick, and Schlein were providing in a paper in 2013. However, again, it's very important to keep in mind that we can, though we have these law of large numbers, we cannot think of psi being simply the purely factorized state of the condensate wave function. Okay, and what we are interested now, what we want to do is to study this convergence in a bit more detail and to get a large deviation estimates for this quantity. Right. And this is based on the following idea. So we already have these law of large numbers for our random variables, which basically says that the probability distribution of these random variables On that I try to sketch here with this blue line is centered around the expectation of the condensate. And what we are interested in now is in the decay of this probability distribution. And for this, we make the ansatz that the probability distribution decays exponentially in the number of particles with a rate that we call lambda. And we are interested now in getting or deriving some effective formula for this rate. So what we have to do is we have to consider the probability that On is bigger than in value x. So N for me is now the centered average sum. I divide by 1 over N. That's from this prefactor here, and take the minus in front. And I want to investigate the large particle limit to get an effective description of these rate function. This is the result I obtain, namely, so I, in the large particle limit, I can prove that this rate function is a leading order given by a quadratic function. And then there are some terms which are at least x to the 5/2. Okay, so let me make a few comments. So first of all, because I only get the first order here, this is only a good approximation whenever x is sufficiently large. So basically what this rate function that I get here tells me is that I can characterize the probability distribution in these dark green regions, so in a large region. However, the rate function is only is only a good describe the probability distribution only in a good way whenever rather close to the condensate's expectation. So this yellow line here is the quadratic approximation I get, and then the red arrow, the red areas, the errors I get from the lower and upper bound. Here, this the other comment I would like to make is about the variance here. So this coefficient again I get for the quadratic term. This is I can compute explicitly. It's explicitly given in terms of the interaction potential and the condensate wave function. And maybe for people who are familiar with these bosonic techniques, so this is completely determined by the Bogoliubov approximation that also Andreas was mentioning before. What is interesting to notice is that is there one sees the quantum correlations through these Bogoliubov approximations. So this variance one gets there is different from the variance one would expect for the purely factorized state because of the quantum correlations. Okay. So the result I get holds for a wide class of operators. However, I have to restrict to operators which are sufficiently nice in the sense that this operator norm is bounded, which basically means I do not only need O to be bounded, but also that the action of the Laplace operator on O has to be bounded in a sufficiently nice way for technical reasons, basically. Right. Then we also proved similar results for the dynamics. So now I define the probability distribution with respect to the ground state of these many-body interacting Hamiltonian, but one can ask a similar question for the dynamics. So starting with an initially pure condensate, one can study or define the probability distribution with respect to the solution of the Schrödinger dynamics, and then ask a similar question, and one ends up with a similar result. So these are results that I obtained together with K. Kirkpatrick and Benjamin Schlein and Robert Saringer before. All right. One last comment I wanted to make is that if one considers the regime of standard deviation, which means that I want to consider x being of the order 1 over square root n, then I recover back central limit theorems that we obtained before. So I can simply plug in what is n times the rate function, and I get exactly this quadratic order, and all the lower order terms, they simply vanish because of scaling. And this is something that was known before, so this was proven by or studied by a lot of authors, as Benarus, Bosman, Kirkpatrick, myself, and Schlein, and many others. So this is somehow consistent with these results or that were widely known before. Right. There seems some question. Okay. Then I would like to go on with at least sketching some ideas of the proof, how we did that. So the proof is based on 2 steps. So the first, what we have to prove first is sort of a generalization of Cramer theorem, because Cramer theorem only holds for independent random variables, where we also know that rate function exists, and both we don't. Once we have that, we can then reduce these bounds that we get on an approximation of the moment generating function that we have to do. Right, so the first step is the following, and this follows from the result I obtained with my collaborators before, namely that in order to get these bounds on the moment on the rate function on the previous slide, it is enough to have sufficiently nice bounds on the moment generating function. And with sufficiently nice, I mean these following bounds here. So as you can see, so this is simply really the moment generating function of our random variables On, and we get some lower and upper bounds, and these lower and upper bounds, they agree in the leading order in lambda, which is quadratic in lambda, and then there are some terms which are either of higher order in lambda or subleading in n. And once one has those bounds on the moment generating function, one gets also the bounds on the rate function on the previous slide. So this is somehow the more the more difficult part to get or to prove, because compared to the central limit theorems and law of large numbers that were known years before, it was enough basically to control the first or the second moment of these operators, and now we really have to have a detailed analysis of the exponential, which is a much more delicate thing to get. Right, and so how to get that? So in order to study these moment generating function in great detail, somehow we have to make sure that we study excitations or all the particles which are not in the condensate. So somehow we want to factor out any contribution of the condensate and really concentrate on the so-called excitations. And this is done by the following observation, namely that I can decompose any n-particle wave function psi n as this sum that I wrote there. Looks like a very complicated object, but if you think of a one-particle function, I think it's easy to understand that a one-particle function you can decompose as one part being orthogonal to the condensate and part that is parallel to the condensate. And now we simply do the same thing, but we decompose psi n as products of the condensates and wave functions that are orthogonal to products of the condensate. And these vectors psi j that are orthogonal to products of the condensate, these we call the excitations. Right, and the idea is that instead of studying psi n, we want to study these vector of excitations. And in fact, it was proven that there's a unitary that implements that, so that really maps our n-particle wave function to our vector of excitations. And we can understand these vector of excitations as being element of an truncated Fock space, it's called. So it's truncated, or it looks a bit different to the standard bosonic Fock space that we have seen before in two ways. So first of all, it's truncated, so the sum usually runs from over all indices j, but here we the sum only runs from j equals 0 up to capital N, which is due to the fact that we start with an n particle wave function, so we cannot have more than n excitations. And this is a very nice property, because usually on the Fock space the number of particles is an unbounded operator, but in our setting on these truncated Fock space it is not. So we can always upper bound the number of particle operator by capital N. And the second thing that is special about these truncated Fock space, that is defined not with respect to L2, but with respect to the orthogonal complement of the condensate in L2. Because we really concentrate only on particles that are orthogonal to products of the condensate. Okay. And why is this useful? Because this unitary allows us to study, instead of psi n being the ground state of these interacting Hamiltonian, the excitation vector. So instead of psi n, we want to study now u and psi n with exactly this excitation vector. And then this is the ground state of these excitation Hamiltonian, that is the original one conjugated with this map un. And the nice thing is that one gets a Hamiltonian that has a very nice decomposition, namely it has a leading order part that I called Q here, and which is quadratic. So that's the reason why I call it Q in creation annihilation operators. It's a bit in the spirit that Andreas was also writing down here. And then we have some remainder terms that come with some prefactors that decay in n. So the hope is to say that we can, in the large particle limit, again neglect the remainder terms, and we are left with a quadratic Hamiltonian. And that's nice from a physical point of view, because quadratic Hamiltonians one has very good knowledge of. So these are exactly these quasi-free states that Andreas was also mentioning. And one can easily do computations with those states. So this will be the idea, that we want to compare our excitation vector psi n with the so-called Bogoliubov approximation, which is the ground state of the quadratic part only. And how to do that is also with a very simple idea of simply interpolating. So we define psi ns being the ground state of gns, which is simply the Hamiltonian that is q plus s plus the remainder. So we interpolate with psi ns between the Bogoliubov approximation and the true excitation vector. And then we control the difference or the error that we do by this replacement simply by a variational principle and Grunwald estimate. Right. So this is the basic idea how that allows us to compute this moment generating function. So to be a bit more precise how we use that, so what we are interested in is really these moment generating functions. So what we do now is to plug in these unitaries that we did before and end up with an expectation with respect to this excitation vector. The problem is that we have to also compute how this unitary acts on the exponential of our observable ON. That is then the exponential, and we get two terms. As we can see here, one is a leading because there's a capital, a square root n in front, which is we consider n to infinity is the leading order term. And we have another term that we consider to be subleading because there's no prefactor of n in front, basically. So the first idea is to get rid of this term that is subleading. The only problem is that it's the exponential of the sum of two operators, and both operators do not commute, so we cannot so easily split them. So how we do that is that we prove some generalization of Baker-Campbell-Hausdorff formula for these non-commuting operators to get rid of that. And then use that we also have some exponential control of the fluctuations to get rid of these subleading term, basically. Yeah.
Question concerning this. So, the trace of e to the a plus b is bounded by the trace of e to the a times e to the b. It's not. mistake that is too large, right?
Yes, I guess that the problem is you always have to take care of the errors you're doing, and it might be that already there you do a mistake that is maybe order square, I don't know, lambda squared.
Yeah, this is true.
But all trace only works for a trace, not for a state, so that's known. So it doesn't help.
Okay.
Oh. Okay. Then once you're there, the next idea is that now we want to somehow use our Bogoliubov approximation. So the idea is that we exactly do these variational idea that we had before. So we interpolate between the excitation vector and our Bogoliubov approximation, and controlling with some variational techniques the difference of them, we then end up with the same expectation of these exponential of this operator in our Bogoliubov approximation. And then that's nice, because I said we know these Bogoliubov approximation, that's the ground state of a quadratic Hamiltonian. So we have very good knowledge of them. We can more or less explicitly compute this operator and get exactly the behavior we wanted to have. I mean, there are several steps where I cheated in this proof. So for example, I mentioned before that for us it's very important to work on these truncated Fock space. And it's very nice because the number of particle operators is bounded, but the disadvantage is that one cannot work with standard creation or annihilation operators on this Fock space, because one has the problem that if one would act with a standard creation operator on an n-particle state, one would map outside this truncated Fock space. So one has to introduce modified creation annihilation operators that somehow preserve the Fock space structure. It's able to define them, and they also satisfy some nice canonical commutation relations, but it's from a technical point much more work, because there are always some corrections that come into play and that one needs to handle when dealing here in the proof. Okay, so far the proof. If there are no questions, then let me go on. So with this proof, what we can do now, so summarizing again, so we arrive at these quadratic large deviation or bounds on the rate function that we have. What is an open question would be very interesting to study is like higher order terms, or even to work towards a full large deviation principle, because for the moment we don't even know whether the limiting function exists, so we really can only compute the leading order of the limits inferior and superior on this rate function. So this seems like a very interesting but also very hard question, because it's not even clear if this Bogoliubov approximation I was mentioning here, or which is relevant for this quadratic term, is enough to get the next order. Also, from a physical point of view, it would be very interesting to go to physical more relevant settings, because now we can only treat like very weak mean field interactions, and from a physical point of view, one would be much more interested in like singular scaling regimes where the particle interacts through some approximate delta interactions. And at least for the second question, we have some partial answers now. And this is what I would like to discuss or give at least as a brief outlook now, what we can do in these scaling regimes. And the setting there is the following. Namely, one study has again the same Hamiltonian more or less as before. So it's again the sum of the potential energy of the particles, of the kinetic energy, and the interaction term, where again one has the 1/n scaling in front. But now one chooses V, so the two-body interaction, to depend also on the number of particles in a very particular way, namely in this way here. So Vn is n to the cube of V times V of n times x. This looks strange, the scaling, but basically it means that in the large particle limit, I want to approximate a delta interaction. So this is somehow a mathematical tool to at least consider some approximate delta interactions. So in the mathematical physics community, we call this the Gross-Pitaevskii scaling regime, because before one ends up as an effective description with the Hartree equations, and here one gets the Gross-Pitaevskii equations. Okay. And one can ask similar questions also here. So it was proven by Lieb and Seringer in 2002 that also in this setting, which is mathematically much harder to study, we still have a law of large numbers of the random variables. And also later we were able to prove a central limit theorem. However, large deviation we can for the moment not do in full generality. So the only thing we can do now is the following theorem, namely we consider a very special operator here. So again, this operator looks very similar to the one I defined before. So again, I sum the operators Qi, so Qi acts as Q on the ith particle as identity elsewhere, but Q now has a very special choice, namely Q is the orthogonal projection on the condensate. So phi is my condensate wave function, and Q projects away from that. And then I sum of all the Qi's. So this is a very, very particular choice, but from the physics perspective, this is a very interesting operator to study. Namely, what it does is that it counts all the particles which are not in my condensate. So again, if we go back to this picture of these Bose-Einstein condensates, so what we expect that most of the particles are in this condensate wave function and zero energy level, and then there are a few particles, these green dots, which are not in the condensates. And n plus, this operator is exactly counting all the green particles. Right, and for this very special choice of an operator, we get the following result, namely for small n being between 0 and capital N, we can prove that the probability that our operator n plus is bigger than n decays exponentially in small n. So, right, this can be understood as a very strong verification of Bose-Einstein condensation, because one way to mathematically formulate Bose-Einstein condensation is to say that the probability that n plus is bigger than capital N converges to 0 when n converges to infinity. And with this upper bound, we prove that. We can even prove some exponential rate now. And this is much stronger than any results that were known before, because before it was known that it decays polynomial, but this was the first result that could even show exponential decay. Right. We can even prove from a physical perspective even more interesting result here. So this is together with Nils Behrmann and Christian Brennecke. So the result I discussed before that I obtained with NUM was again for the Bose gas restricted to the unit torus. But together with Christian and Nils, we can now also prove the same result where we consider the gas in 3 dimensions, but trapped within trapping potential. The techniques are very similar, but as also Andreas already mentioned, simply the analysis from a mathematical point of view gets much harder if you're not on the torus. Right. And one can also, from these exponential bounds that we got, one can also get some sort of large deviation result for this operator n plus. So what we can prove is that again, the logarithm of the probability that n plus minus its the so-called quantum depletion, which is the asymptotic expectation of the number of excitations. The probability that this one is bigger than small n can be rewritten as the infimum over all lambda of this function here. So it's minus lambda n, and then we have a term that is quadratic in lambda, and again invariance, and some higher order terms that are at least cubic. So this looks very similar to the large deviation estimates we had before. So again, we can, based on these bounds that I showed on the previous slide, we can again get some quadratic large deviation estimate in the setting here. However, here we only get the upper bound. Right, so how to get this is again by a bound on the moment generating function that we have for the operator n plus. And we also use a norm approximation that was provided by Boccato, Brennecke, Chenat-Yampo, and Schlein in 2018 for the ground state that allowed us to compute that. Also, last year I was able to compute, really compute the moment generating function in the large particle limit. So I was able to not only show these upper bound up to second order, but I can even now compute the full function lambda here, now in the large particle limit. Right. However, it's still open whether this is also a lower bound, and right. And also, like what would also be very interesting is to understand whether in these singular scaling regime of these Gross-Pitaevskii interactions, one can also hope for large deviations for general observables, not only for n plus that we are able to do here. Okay. So there are no questions, then let me come to my last slide that is about another outlook I want to formulate, namely together with Lorenzo and Daniel, we also had considered the empirical measures of these random variables we discussed before. So we considered the empirical measure in UN, that is simply the empirical measure associated with random variables ON we discussed before, and we compared it to the measure that the condensate gives rise to. And what we can do for the moment is that we can prove some law of large numbers in the Wasserstein-1 metric. So we prove that this, again, that the improbability, the Wasserstein distance of these empirical measure of the many-body state compared to the one of the condensate wave function converges to 0. And what we are currently working on and what would be really interesting to get is whether we can also hope for large deviations and some sort of Sarnoff type estimates in that setting here. So with that, I would like to thank for your attention.